First, I would like to thank Hannah and Driss for giving just about everything that could go into my talk. And because there isn't a whole lot that you can say about carbon and main belt asteroids. And with those constraints, in other words, I'm not looking at comets, I'm not looking at meteorites, I wasn't looking at the outer solar system, I'm not looking at Ceres necessarily, although I've thrown it in. It really came down to about 2 areas that I wanted to talk about. And I will be able to talk very quickly, I think, about the first area because the last 2 speakers have spoken already about it. So thank you. And maybe I'll be able to catch up for everybody a little bit also. I threw in Amanda and Andy Rivkin because at various times they've given me some help in this discussion. The fact that you didn't get an abstract from me has a lot to say with how much we don't really solidly know about carbon in the main belt asteroids if we're looking sensu stricto at the asteroids themselves, not meteorites, not making assumptions, but looking at what we can derive from data from the asteroids themselves. So, and carbon, not other things, just carbon. Okay, so what constitutes an identification of carbon in main belt asteroids? I decided that we would look at albedo, and of course there are darker asteroids. We look at background slope, if you will, but the slope in and of itself is not necessarily diagnostic of a whole lot. So I went to look for absorption features of some sort or another and use that as my criteria that I was looking at. So I've had 2 findings, as I said. And the first has been covered by the last 2 speakers as well, which is the sort of concurrent observation by 2 different research groups, both Campines and also Rivkin and Emery, on the detection of ice and organics on 24 Themis on its surface. And 24 Themis was targeted because it had I think at least 3 of the smaller main belt comets, the asteroids that are starting to outgas, were part of the family that 24 Themis anchors. So it became a target of great interest for observers, and both groups observed it, and both groups came up with results that would indicate both water, ice, and organics. This is from Campines et al. He took these are observations that are grouped together into 4 sets that cover the rotational period of the asteroid. No pole position was available at that time. And it shows that there is a feature that's broad and it's shallow, centered near about 3.1 microns. That's very similar to what you would get if you had small-grained water ice. He also pointed out that there were other features that longer wavelengths that matched. There was not a great change from one portion of the surface of the asteroid to the other. So if you make the assumption that you are looking at each side, they're all very similar. Those are all from about 3.3 to 3.5 microns. They were very similar to aliphatic pH stretching modes, and concluded that that may be what is present. However, going on to Rivkin, and here's Rivkin's spectrum, and a fit that he did to the spectrum in order to be able to remove, again, a very good match to what would look like water ice, solid water ice, also not looking like any of the rest of the infrared spectra that are normally obtained around the C-class asteroid or C-complex asteroids. Using that fit, and removing that fit allowed them to look for organics and additional information about the organics. You've seen this spectrum also. I think it was in Hannah's presentation. What's most interesting about that is that in both spectra, there is some activity near 3.3 microns that might indicate that there's an aromatic component to this also. That difference and the significance of the aromatic and aliphatic components was brought home earlier, I think by Dale, me. But they both agreed. They both showed different things. There was evidence of organics and evidence for water ice. Seems that the one method for which, or they kind of agreed, I think, at least Campines argued for, and I didn't see anything that precluded that was that so in order to keep this going, it has to be a thin layer of water ice on top of the organics, and there must be some probably internal source for the outgassing that would continue to keep the water ice there, but not let it be too thick. So I thought that was interesting. If Andy were on today, I'd ask him to comment about all of this, but he did over the email to me earlier. Okay, so let me go on to the part that I probably know a little bit better because I worked on it with Amanda, and that is to take a look at the UV. So starting with taking a look at some spectra of terrestrial coals and carbon compounds in the spectral range from about 0.35, 0.36 to 0.8 microns. They're pretty featureless. And if you we've blocked out the UV here. If you show us the UV, you start to see additional information, which is going to change depending upon how much the material has been processed. The processing route being the graphitization or removal of hydrogen from that material. So we want to look for that. First of all, let me talk about Ceres, even though I've declared it as not an asteroid for the occasion, and everybody has talked about Ceres to some extent. We also looked at it with the Hubble Space Telescope and matched it in the lab to two candidate materials, both a glassy carbon and an anthracite that we observed, and we're looking at the normalized reflectance here, so that we could join together all of the spectra themselves. This is from paper Hendricks et al. 2016, and we had some significant matches. But one of the reasons that I showed this to you was that in the next slide, we again blocked out the shorter wavelengths for the HST spectrum and compared it otherwise in wavelength and in strength to both ground-based spectra in the visible region and to IUE spectra that were obtained by Rutger and Brody in the 1990s, and determined that the basic shape and strength of them were similar, and we felt that we could use that as a premise for going ahead and taking a harder look at the IUE spectra, in other words, revisiting them, which we did. And these are all of the primitive spectra that we've looked at, or the asteroids with primitive spectra with their sort of basic classes on them. IUE, and then whatever else we pulled out to analyze with it, but it was the IUE was the ultraviolet side of this, and we went to take a look at it. And we're still in the middle of doing this, so there's a part of this that is work in progress, and at least that's going to be somewhat of my excuse. But one of the reasons I wanted to show this, without going into great depth on the different characteristics of these different classes of asteroids, is that across the spectral region that's visible and the very near IR, you do see some differences, and they are classed differently. You see that the B class looks like it has a blue slope or decreasing reflectance with increasing wavelength. Basic C classes are pretty featureless with the turnover in the blue near UV. CGs are stronger. CGHs and CHs show a rough absorption around 0.7 microns. That in the past has been attributed to possible aqueous alteration of the surface material. So bear those in mind when we look at the spectra that we took from the IUE and combine them with the other spectra from the visible wavelength region. We note that, in fact, if you look at the B-class asteroids, they're pretty featureless in the visible, but they have that turnover at albeit a shorter wavelength in the UV. These blue lines through these spectra show where a cutoff is for what we see in our visible spectra from the ground-based and the IUE spectra. They also show some of a turn up here sometimes. They all look very different, basically, for the B-type. There's some pretty major differences there. The C classes, the basic C classes, look very similar, and they have sort of a weak feature in the UV at turnover. CH types, of which we had a fair number, are generally the same sort of thing. They're flat, they're red, they match a lot in the UV. They have the absorption feature near 0.7 microns, and they all look very similar. CGHs, which are rarer, we have two of them here, and we're seeing a significant difference between the CGHs down in the UV. And that would be a stronger absorption, I guess, near 0.7 microns. So we asked in sort of a general sense when we're doing this work, which is not just related to carbon, but good enough for the occasion, why do some of these asteroids have a somewhat less pronounced UV absorption than others? Why do the B types have less of a UV absorption than the C complex? They do have an absorption, it's just at shorter wavelengths, so why is that there? And we assume that for most materials, the main cause of the UV absorption is the FeO charge transfer transition that occurs, the IVCT. So, but what's causing the difference of these? And we hypothesized at the moment that among the low albedo asteroids, the UV absorption will be affected by the presence of opaque weathering products. And so we went to test this by doing some spectral models, interconnecting models of phyllosilicate. In this case, we took a serpentine, which is probably the most commonly found in CM2 carbonaceous chondrites, and an amorphous carbon. And we got some matches. What's important to note from this is that preliminary, that our matches took and seem to require a large percentage of carbon, which we had people say to us, of course, that's not possible. We don't see that in the asteroids or in the meteorites, so we're not expecting to see this much carbon. Go back to your drawing board. And so we're in the process of work on that drawing board, and I will show you that we thought, what else can we vary besides composition, and we need to be able to ensure that we get a dark enough spectrum, the darkening agent being the carbon, and if we don't need that large amount of carbon, what we did was vary particle size mixtures. And particle size mixture modeling reduces the percentage of carbon we needed to produce these spectra. And we're now getting down into the ballpark, and we're beginning to show some of these turn-ups that we have seen in a couple of the spectra from the IUE. And so basically, we're still mixing, is what it comes down to. And I hope that catches us up a little bit on time. Thank you.
Who has questions?
I have a question.
Sure.
Can you clarify what kind of carbon have you used here?
In the model?
In the model.
Oh,
and also, you said that obviously there is a strong effect in terms of particle size. In the last slides, what kind of particle size you were using?
So I'll answer that, Faith.
Okay.
We used an amorphous carbon, the one from Rouleau, one of the ones from Rouleau and Martin, okay. 1991. And for grain sizes, we're still, fiddling with it. They have a big effect, but we're using tens of microns in grain sizes for the two different components of the model. And seeing what mixtures retain a little UV absorption edge and get dark enough. We see on the target bodies variations in the UV drop-off strength, right? And so we want to be able to match that and match the albedo.
Yeah, and when you say 10, something like between 10 and 50? Ballpark? Yeah. Okay.
Stand by.
Yeah.
Definitely still in work.
Yeah. I have a question in the chat box. What is the difference in the particle sizes between the amorphous carbon and the serpentine?
Again, that's in work, but right now we're doing things where they are each tens of microns. So I don't know exactly which were in the models that Faith showed, but say 10 microns for the serpentine and 20 microns for the carbon might be an example of what we use. So we're fiddling around to see what the effects are and what makes sense. But it's not final yet.
What makes sense for us for a little bit was basically to start considering how our matches end up matching kind of with the carbonaceous, the CM2 carbonaceous chondrites, CI, whatever the carbonaceous chondrites are, we're using them as sort of as guides. What makes sense otherwise, in other words, that's why we wanted to reduce the percent of carbon we had in the sample. that was of interest to me because the other option, of course, is to consider whether or not there is a large amount of carbon material on the surfaces of the asteroids, and that then would require the large percentage of carbon in the surface material if we're not probing deeply into the surface of the asteroid, which we aren't with spectral reflectance. And that was what another option that we had was to consider, well, maybe we really do have that amount of carbon. I would not necessarily have thought that. I'm not going to rule it out either. There's a lot of variety in the solar system. But I was interested to note that the modeling of the reflectance spectrum that Rivkin and Emery did required something like 70-some-odd% carbon in the surface. So I'm not convinced that we aren't seeing a large amount of carbon in there, but I don't know. And there's a question from there.
Well,
I don't know if that answers Diane's question.
In case I want to comment on what you're just saying
Sure.
there, that I think it's interesting that Andy and Josh needed 70% carbon
Right.
in their model.
Right.
And some of ours, we need that much if we don't do too much fiddling with grain size. And to me, how much extra carbon would we expect there to be on the surface compared to meteorites? Maybe it's natural to think that there should be some extra carbon, more carbon on the surface than in the meteorites, perhaps due to weathering processes.
Let me answer Jeff's question as much as I can, which is that's what we're trying to do, I think, kind of right now. The question was to distinguish the general spectral influence of FeO charge transfer versus the usual carbon-based UV absorption, and where they show with these turnovers are at 300 to 400 nanometers. And that is what we are working on trying to do, I think, right now. One of our most serious problems that we have down at that wavelength is a lack of reasonably acquired optical constants for materials. And so we're a little bit more limited in what we are able to use until we get more materials too. So, but we're trying to do that. I don't know that we have done that yet, but we're trying.
But also, Jeff, I think for the amorphous carbon that we're using, it's pretty featureless down to 0.2 microns. Maybe there starts to be a little turn up there, but most of the absorption that we are seeing in the asteroid, we are assuming is due to the serpentine or whatever phyllosilicates. But on some of them, we do see sort of a bowl-shaped absorption that we think maybe could be because of that turn up in the carbon at the shorter wavelength.
You're welcome, Jeff.
Perhaps we will wait for Jeff to type and then we will move on.
Yes. Yeah, that absorption, we think, is mainly due to that IVCT band, charge transfer band.
The main, yeah, and that's an iron absorption, yeah, as a rule.
Okay, so we will move to the last talk on the